Let's get started. In the previous lesson, we looked at the substitution rule for indefinite integrals, which is going to be an invaluable tool as we work on integrating different functions. There is also a substitution rule for definite integrals. Those are integrals that do have limits of integration that we evaluate everything for. And it ends up being very similar, but there is an extra step. So let's take a quick look at this rule, and then we'll do a couple of examples. Now, it might look a little bit scary at first because there's a whole lot of things going on here, but it's not that much different from the substitution rule for indefinite integrals. The only main difference is that we have limits of integration going on. But if you ignore those, it looks exactly the same. So let's take a look at this. If g prime is continuous on the closed interval from a to b, and f is continuous on the range of u equals g of x, then the integral from a to b of f of g of x, g prime of x dx, is equal to the integral from g of a to g of b of f of u du. The only thing that's different here for our substitution rule is that the limits of integration change. If we start with x equals a and x equals b, we know that u is g of x, and so basically we need to see what the values of u are that correspond, because if we've changed things so that we're integrating in terms of u, we have to change the limits so they're in terms of u. This probably looks intimidating. I promise it's not that bad. Let's take a look at an example. Evaluate the integral from 0 to 4 of the square root of 2x plus 1 dx. This is an integral that we can use the substitution rule on. We're going to use that inner function, so we're going to let u equal 2x plus 1. If we do that and we differentiate, we get du equals 2 dx. And because we only have a dx here, not a 2 dx, we're going to divide both sides by 2, and that gives us 1/2 du equals dx. So what we can do there is we can make that substitution. So this integral, which I'm going to rewrite down here, the integral from 0 to 4 of the square root of 2x plus 1 dx. If we go ahead and change that in terms of u, this is going to be the square root of u. And our dx was 1/2 du. So we're going to put the 1/2 out front and the du here. But the thing is, we can't keep the limits as 0 and 4 because those were values of x, and now we need the corresponding values of u. But this is very easy. If we look at that upper limit 4, if x equals 4, well, we know that u is 2 times x plus 1. So we can write 2 times 4 plus 1. And we know that that equals 9 because 2 times 4 is 8, and adding 1 gives us 9. So that tells us that when x is 4, the corresponding value of u is 9. So if we look back at our upper limit of integration, it was 4 for x, but we know that the corresponding value for u is 9, so we can write a 9 up there. And then we do the same thing for x equals 0. U is 2 times 0 plus 1, which is going to be 1. So that means that when x equals 0, the corresponding limit for u is going to be 1. And once we've rewritten everything in terms of u, including the limits of integration, then we can go through and take that integral. So we're going to keep that 1/2 out front, and then the square root of u is the same as u to the 1/2, and we know the integral of that is u to the 3/2 over 3/2, which is the same as 2/3 u to the 3/2. We've done that several times, so hopefully you remember that. We don't need a constant because this is a definite integral. And when we have a definite integral, those constants are going to cancel. We also can see that the 2's are going to cancel. And so we end up with 1/3 times u to the 3/2 power, evaluated at 9 and 1. So that's going to be 1/3 times 9 to the 3/2 minus 1/3 times 1 to the 3/2. And then 9 to the 3/2, well, the square root of 9 is 3. And when we cube that, we get 27. But then when we divide it by 3, we get 9 again. So this term ends up being 9. And then minus 1 to any power is 1. So that's going to be 9 minus 1/3. 9 is 27/3, and 27/3 minus 1/3 is 26/3. So in the end, we've got our answer of 26/3. That is what the substitution rule for indefinite integrals says. We convert everything to u, and then we can go ahead and integrate in terms of u, and we never have to go back to x. We never have to back substitute x back in, so long as we take the original limits, which were in terms of x, and rewrite them, recalculate them, so that they are in terms of u. There is another way to do this. I don't like that as much as this. You could use the substitution rule for indefinite integrals. You could ignore the limits of integration. You could go through and do the integral using the substitution, getting all the way back to here, and then you could replace u with 2x plus 1. And then once you've got that, and it's going to be a more complicated expression, you could plug in the original limits of 2 and 4. But I think it's much nicer to take the limits in terms of x and switch them so that they're in terms of u, instead of taking this antiderivative that's in terms of u and sending that back to x. Because then wherever there's a u, it's going to be 2x plus 1. It just ends up being a little bit messier there. It's a lot easier if we just switch everything over to u. Okay? Now I don't have room for another example here, so I'm going to make that the next video.